So if you're in the machine learning world, you've definitely heard about reinforcement learning, or RL. And it's often talked about like it's this completely separate, almost mystical field, right? Well, the entire point of this explainer is to just tear that wall down. We're going to show that if you really understand supervised learning, you are already 90% of the way to understanding some of the biggest ideas in RL, including RLHF. Let's just dive right in. You've heard this one before, I'm sure. It's one of the first things people say to draw a line in the sand between RL and standard supervised learning. It paints this picture of a world with no ground truth, where a model is kind of fumbling around in the dark, guided only by these abstract things called rewards. And this is the other half of that classic RL pitch. No nice, neat, static data set like ImageNet. Nope. Instead, the model is out there, interacting with some environment, creating its own experiences. And when you put these two claims together, it really makes RL sound like a totally different beast, suggesting that all of our hard-won intuitions from supervised learning just don't apply here. Let me just be blunt about it. This whole way of framing things is not just unhelpful, it's actively misleading. It builds this artificial wall between two fields that, when you look at the math, are just deeply, fundamentally connected. And our goal here is to completely break down that wall. So, here's our game plan. First, we're going to translate the RL jargon into ML terms you already know. Then, we'll zero in on the one core technical problem that algorithms like Reinforce were actually invented to solve. After that, we'll unpack the algorithm and its formula, and this is the really crucial part. We'll see that it's just a clever, reward-weighted version of the exact same gradient you use for cross-entropy loss. Finally, we'll look at how this applies to things like RLHF and talk about the one big complication that does make RL a little different from your standard training loop. Okay, part one. I want you to think of this section as a Rosetta Stone. We're going to take all that specialized vocabulary from reinforcement learning and just map it one-to-one into the language of supervised machine learning that you already speak fluently. Let's just go through this table. When you see the word policy in an RL paper, they're just talking about your model. It's the neural network. An action? That's just the model's output, the prediction, the next token it generates. A reward? That's just a numeric label, a score you give to that output. A rollout or a trajectory sounds fancy, but it just means generating a sample sequence. And the environment? That's simply the thing that gives you the score, an evaluation function, a data source, whatever. See? These aren't new concepts, they're just new names. A lot of this vocabulary came from different fields, things like control theory or psychology, which is why it sounds so different from the stats-heavy language we're used to in supervised learning. Okay, let's take on that first myth. We don't have data. The story goes that we generate experiences, but what really is an experience? Let's say you have an input prompt. Translate this sentence to French. Your model generates an output. Then, some external function gives that translation a blue score. So what do you have? You have an input, an output, and a score. That is a data point. The fact that your model generated the output part of that data point doesn't magically make it not data. It's just self-generated data. And what about that whole no labels thing? The claim is we only have rewards. But a reward is a label. It's a numeric score attached to an output. I mean, think about it. If we train a model to predict house prices, the target price is a numeric label. If our language model generates an output and gets a blue score of 0.82, well, that 0.82 is a numeric label for that specific output. It's the exact same idea. Okay. So if RL is just ML with a fancy vocabulary, then why do we even bother with special algorithms like Reinforce? Why can't we just, define a loss function and backpropagate like we always do? This next section gets to the absolute core of the real problem that RL was actually invented to solve. This is the 100% correct and natural question to ask at this point. If what we actually care about is maximizing a blue score for translation or getting great ratings from humans for our chatbot, why don't we just make that our loss function? Just minimize the negative of the score. We want outputs with higher scores, so we should just backpropagate the score through the model, right? And this slide really gets at the fundamental mismatch in so many of the tasks we care about. We typically train our models with cross-entropy loss. All that does is push the model to perfectly mimic the very next token from some reference text. But then when we go to evaluate the model, we care about these much fuzzier, higher-level things. Does it sound good? Does it capture the right meaning? Did the code it generated actually compile and pass the tests? We're training for one thing, but we're evaluating for something completely different.
The reason we can't just set our loss equal to, say, the negative blue score is because the whole pipeline, from the model's weights all the way to that final score, is non-differentiable. The first place the chain breaks is in the sampling process. Your model outputs these nice, smooth probabilities for the next token, but to actually generate text, you have to pick one. You have to sample a discrete token, usually with an argmax or something similar, and that operation has zero gradient. It's like an election. If one candidate has 50.1% of the probability, they win. But a tiny little nudge in the probabilities could cause this huge discontinuous jump to a completely different winner. There's no smooth path, no gradient across that cliff edge.
The second place the differentiable chain breaks is the metric function itself. So even if we somehow had a differentiable way to sample, metrics like blue or number of unit tests passed are fundamentally just counting things. They're integer counting functions, so their gradients are zero almost everywhere, and then they jump to infinity right at the points where the count changes. They're step functions, not these smooth rolling landscapes that gradient descent needs to work. You just can't take a derivative of the number of friends who have a birthday in March. So here we are. We have this really fundamental problem. The objectives we actually care about are non-differentiable. And this is where REINFORCE comes in. I want you to think of it not as some brand new, complex, alien algorithm, but as a really, really clever and elegant workaround to this one very specific problem. In plain English, the core idea is shockingly simple. First, you just use your model to generate a few complete outputs. Second, you take each of those outputs and get a score for it using your non-differentiable metric. Third, and this is the key, for each output you generated, you calculate the gradient as if that output were the ground truth, just like in normal supervised training. You're basically asking, what changes to my weights would have made this specific output more likely? And then, step 4, the trick, you just multiply that gradient by the score you got. That's it. Outputs that got high scores get their gradients scaled way up. Outputs that got low scores get their gradients scaled way down, or even pushed in the opposite direction. All right, now let's actually look at the math behind that simple idea. And don't worry, we're going to unpack this thing one piece at a time. We'll connect every single symbol here to concepts that you're already an expert in from all your work in supervised learning. Here it is. This is the REINFORCE update rule, which is at the heart of the policy gradient theorem. So on the left, we have the gradient of our objective function. That's the direction we want to move our model's weights. The formula tells us that this gradient is the expected value of two things multiplied together, the reward R and this other term here, the gradient of the log probability of our action. Let's really unpack that second term. Okay, let's start with the very innermost piece, pi, of a given state. In RL, they call this the policy. For a language model, this is just the probability distribution over the next token. So given the state S, which is the text so far, like the cat sat on the policy pi gives you the probability of taking action A, which is picking the next token, like Matt. This is nothing more than the standard softmax output of your language model. Nothing new here at all. Now let's add the gradient and the log. This whole term is basically asking the question, if I make a tiny change to my model's weights theta, how does the log probability of having chosen this specific action A change? Well, guess what? This is just standard backpropagation. For those of you who want the details, this form actually comes from a really neat mathematical trick called the log derivative trick, which lets us get the policy's gradient without having to differentiate through that messy, non-differentiable environment. But the key takeaway for us is that this is the exact same gradient vector that you compute when you're calculating a cross-entropy loss. And finally, we have R, the reward. This is just a single number, a scalar. It could be a blue score of 0.65. It could be a human rating of 4 out of 5. It could be the fact that the code you generated passed 7 out of 10 unit tests. The most important thing here is that R comes from some external source, and we do not need to know how to differentiate through its calculation. It's just a constant that we use to multiply the gradient we already calculated. It just tells us how much we should reinforce a particular output. Okay, this is the big reveal. This is the payoff. We've defined all the individual pieces. Now we're going to put them together and put the REINFORCE update rule right next to the standard cross-entropy loss that you use every single day. And this is where the connection becomes absolutely undeniable. Just look at this. On the left, we have cross-entropy loss. The gradient you use for training is proportional to the negative gradient of the log probability of the correct action, the ground truth. Now look at REINFORCE on the right. The gradient update is the negative gradient of the log probability of the sampled action, whatever your model happened to spit out, scaled by the reward R.
The core mathematical object, that Dalla log pi part, is identical. The only things that are different are which actions probability are we trying to push up and by how much. In supervised learning, it's the ground truth action, and the multiplier is just 1. In reinforce, it's whatever action you sampled, and the multiplier is the reward. It is, quite literally, reward-weighted supervised learning on your model zone outputs. So now that we've pulled back the curtain on the core algorithm, let's talk about where that reward signal, that R, actually comes from in the real world. This will lead us straight into reinforcement learning from human feedback, or RLHF. And then, after that, we'll talk about the one major complication that really does make this a bit different from standard supervised learning.
So how does RLHF actually work? Well, it's this really clever 3-step process. First, you collect a bunch of data by asking humans a simple question. Here are 2 responses. Which one is better? Second, you use all of that comparison data to train a totally separate model called a reward model. This model learns to predict a score for any given response so that the response humans preferred always gets a higher score. Then, for step 3, you just freeze that reward model and use it as your automated scoring function. It's the thing that provides the reward R during the reinforced training loop.
And this is a great illustration of how flexible the reinforce algorithm really is. That reward, R, it can come from anywhere. It can be a cheap and fast automatic metric like blue, but that might not actually capture what you care about. It could be a direct score from a human, which is super high quality but incredibly expensive and slow. It can come from a learned reward model like an RLHF, which is way more scalable, but is still just an approximation of true human preference. Or it could even come from another AI. The core logic of reinforce doesn't care. It just needs a number.
Okay, but now for the one key complication. In standard supervised learning, you have a fixed data set. The data distribution is stationary. You just iterate over it again and again. In RL, that's not true. You generate data with your current model, and then you update that model. Well, that updated model is now going to generate a slightly different distribution of data. This non-stationary shifting data distribution is the one true deep difference from the typical supervised setup. And it introduces some serious challenges. Your model can get stuck in these feedback loops, only generating data from one tiny part of the possible output space. And that's why concepts like exploration versus exploitation are so critical in RL. You have to make sure your agent keeps generating data to learn from, which is a problem that just doesn't exist when you have a fixed data set like ImageNet.
So let's bring it all the way back around and look at those initial claims again. They say we don't have labels, only rewards. The reality, rewards are labels. They're just numeric scores. They say we don't have data, we generate experiences. The reality, we do have data. We just generate it ourselves on the fly. And the big one, RL is fundamentally different from supervised learning. The reality is it's gradient descent with reward-weighted updates using the same log probability gradients you already know and love.
And that really is the ultimate takeaway here. The 2 communities might have developed in parallel, using totally different words for the same core mathematical ideas, but the underlying machinery is the same. If you have a solid grasp of modern deep learning, gradient descent, backprop, cross-entropy, you are perfectly equipped to understand these powerful RL techniques. So don't let the different vocabulary convince you otherwise. Your intuitions are far more powerful and transferable than you've been led to believe.